Building a 3D bioprinter for tissue engineering involves integrating mechanical, biological, and software components to fabricate complex tissue structures layer by layer. Here's a structured guide on how to approach the development of a 3D bioprinter for tissue engineering. Understanding 3D bioprinting in tissue engineering. 3D bioprinting combines additive manufacturing principles with biological materials, e.g., cells, biomaterials, to create intricate tissue constructs that mimic native tissues. It enables precise control over spatial distribution and organization of cells and biomaterials to replicate biological structures. Steps to build a 3D bioprinter for tissue engineering. Design and fabrication of bioprinter components. Printer structure. Design a robust frame and gantry system capable of precise movement in 3 dimensions, X, Y, Z axes. Use materials compatible with biocompatible standards and able to support printing heads and extrusion systems. Extrusion systems. Select extrusion systems based on the type of biomaterials and cells to be printed, e.g., pneumatic, syringe-based, or extrusion using pressure-driven methods. Bioprinting technology and techniques. Printing heads. Choose printing heads suitable for dispensing bioinks containing cells and biomaterials. Optimize nozzle sizes and configurations for precise deposition and resolution. Bioinks. Develop or select bioinks composed of biocompatible materials, e.g., hydrogels, polymers, that support cell viability, proliferation, and differentiation during and after printing. Integration of control and software systems. Motion control. Implement motion control systems, e.g., stepper motors, linear actuators, and drivers to coordinate precise movements of printing heads and stage positioning. Software interface. Develop or configure software for CAD, computer-aided design, modeling, slicing, segmenting 3D models into printable layers, and G-code generation for controlling bioprinter operations. Biological compatibility and sterility. Sterilization protocols. Establish sterilization protocols for bioprinter components and printing environment to maintain aseptic conditions and prevent contamination of bioinks and printed tissues. Cell viability. Optimize printing parameters, e.g., extrusion pressure, printing speed, to preserve cell viability and functionality throughout the printing process. Post-processing and tissue maturation. Cross-linking and curing. Implement post-processing steps such as cross-linking or curing to solidify printed structures and enhance mechanical properties of printed tissues. Cell culture and maturation. Transfer bioprinted tissues to incubation systems that mimic physiological conditions, e.g., temperature, pH, nutrient supply, to promote cell maturation and tissue integration. Advanced applications and considerations. Multi-material printing. Explore multi-material printing capabilities to incorporate multiple cell types, growth factors, and biomaterials within complex tissue structures. Vascularization. Develop strategies for bioprinting vascular networks to support nutrient exchange and tissue perfusion in larger constructs. Challenges and future directions. Biological complexity. Address challenges related to replicating the complexity of native tissues, including cell-cell interactions, tissue architecture, and functional integration. Scale-up and commercialization. Scale up bioprinting processes for clinical applications and navigate regulatory pathways for approval of bioprinted tissues for transplantation and regenerative medicine. Conclusion. Building a 3D bioprinter for tissue engineering requires interdisciplinary collaboration among engineers, biologists, and clinicians to integrate technological advancements with biological principles. By optimizing printing parameters, enhancing cell viability, and advancing tissue maturation techniques, researchers can advance the field of tissue engineering towards developing functional, implantable tissues and organs. As bioprinting technologies continue to evolve, innovation in biomaterials, bioinks, and printing strategies will play a pivotal role in shaping the future of personalized medicine and regenerative therapies.